Our next speaker is Tanja Schindler from the University of Vienna, currently visiting the University of Pisa. And she's going to talk about a quantitative central limit theorem for certain unbounded observable over piecewise expanding interval maps.
I hope I'm better hearable now. So this work is joint work with Casper and Fernando, and well, he is basically the successor of me in Pisa, and for some formal reasons we had overlap of 2 weeks in which we started this project. So it's nice to come back to Italy to present it. And well, I already tried, the technique is working. But first let me give the setting. So I will first talk about the setting and, well, giving some applications why I'm actually studying these functions. And then we will look at the qualitative central limit theorem and the quantitative version of it. Okay, but let me first introduce the setting. So we look at an interval and we partition it into only finitely many intervals, and well, starting with 0 and 1. And we look at a class of maps which maps the unit interval into itself. It's the following property. So the map is full branched, so all these intervals are mapped to the whole interval, and we can just write them in such a way. And furthermore, they are C2 and strictly increasing, so we only allow positive slopes, and also the inverse of the single maps has to be differentiable, and the map has to the inverse has to be the derivative has to be uniformly Hölder continuous. And in this case, we also have that there exists a maximal gamma, which we will need later on. So one example would just be to look at some nx mod 1, or just the simplest example, the doubling map, which was also seen today already. And important thing to notice is that 0 and 1 are actually fixed points in this setting. So, well, a lot of people here have studied piecewise expanding interval maps, so often you have more flexibility, but well, we have to restrict ourselves at the moment to have finitely many positive slopes, and they have to be full range. So, I mean, what we are looking at is basically just something which looks like this. So you have some slopes, they don't behave too chaotic, and they are all positive, and you fix 0 and 1 are fixed points. Drop this. And I think I would not wanted to put it here. And now we are looking at observables which behave chaotic at 0 and 1, which means that their lim sub can be infinite and their lim inf can be minus infinite. So we have might have something which, no, I shouldn't have done this. Okay, now it works. So if we have 1 here, we have something which behaves in the middle quite regularly, but now at 0 and 1 it can behave very chaotic. So this would be a map we would be looking at. And I'm sorry. I tried it out, but it takes a little bit of time to learn it, to just remember it, what to do. And so what we want to do is to prove a central limit theorem for such kinds of maps. So with the observable chi and the transformation psi, just as we had it. And well, this is what I mean with a central limit theorem. So Peter has just talked about central limit theorems in a general way, but here we actually want to have a norming sequence, square root of n. And in the second part, we will also be interested in a speed of, if we have a central limit theorem like this, we will also be interested in some speed of convergence result. And well, just to give a very brief recap, and I think probably I'm starting now boring some people, but it's a little bit late, so people can't concentrate anymore anyway. So I mean, if you have if you just look at the strong law of large number, if your psi here is ergodic, then things are really easy, as long as chi is integrable. But with the central limit theorem, we just need a lot of different methods, and we can't do it immediately. But before we look at the results and the methods how to prove it, I want to give you some motivation why. I mean, that time this was me studying these things, and I just came back from a number theory conference and was interested in these things. So the question is, why are we actually interested in exactly these kinds of systems? So, and with that I can also give some connection to the name of the center. So in recent years there has been some interest in sampling the Riemann zeta function. So, well, for the following we call, by zeta we always denote the Riemann zeta function. And what we want to do, we want to look at the sample along a vertical line z equals s plus ER. So we just, yeah, you have to press very hard. This is the trick. So I mean, you have here one, and then, well, you fix your S and say like your S is something like this, and then you are interested in values along this line, and you are particularly interested in values on the critical line, which is S equals 1/2. And so, yes, this is just what I said. The interesting point is, particularly interesting point is z equals, s equals 1/2. And, well, why are we actually looking at these values? So, it's long known that the non-trivial zeros of zeta can only be in this critical strip. So I mean, it's somehow interested to see how values in this area behave. And so, but what exactly do we mean by sampling? I just said, okay, we take a one strip and we look at the value. So what do we mean by this? So what we look at is we look at the sum of this zeta function of s and fix this s plus I times some random variables, and then we take the sum over it and look, well, in this case this would just be a mean value and some references. So the first people who were looking at such system were Lifshitz and Weber, and well, they fixed it for z equals 1/2, and for this zk they just looked at the Cauchy random walk, so there is no dynamics in it at the moment. And well, and they proved that this converges to a finite limit. And well, then Johann Steuding, he is a number theorist. He went to Japan and he actually wanted to work with some number theory people. This is the story I got to know, but there were only people in ergodic theory, so he started to collaborate with people from ergodic theory. And then he was like, okay, well, instead of looking here at the Cauchy random walk, he was looking at this for ergodic transformation. And so he was looking at this Boolean type transformation. I will show a picture on the next slide. And he just said, okay, well, for this set K, he just looks at the iterates of this transformation. And so this thing here is this Boolean type transformation. For people who know the Boolean transformation, the difference with the Boolean transformation is that for the Boolean transformation we don't have a factor 1/2 here, which now changes things a lot, because for this transformation here we have a finite invariant measure.
It's not conjugate to 2x mod 1.
Exactly, yes. This. Do you want to give my talk?
Tomorrow.
No, this is basically what I'm going to say in the, well, am I going, I think, then you can just apply Birkhoff's ergodic theorem and get the statement, of course. So it was, what Johann Steuding did was more from the number theoretic side interesting than actually applying methods from ergodic theory. Well, then I met a number theorist who was working with Johann Steuding, and he was also interested in these kinds of results. And then we were thinking, okay, well, if you look from a statistical point of view, usually a strong law of large numbers does not tell you that much. So we also wanted to have a central limit theorem. And well, then in this case, what we now look at, we don't look at the complex central limit theorem, but we just look at this for the real and the imaginary part separately. And now, yeah, John wants to overtake. What we actually do is we look at the conjugate system, which is 2x mod 1, the doubling map. And well, we have that this is conjugate by this map. And so we can, I state the reference, but I think it was actually already known before Karpatsky actually wrote it down, but they did not a nice reference. And then, well, one can just study the zeta function composed with this doubling map instead of the original system. So if we have some function h composed with phi, and we can instead study h composed with this bijective map xi and apply this doubling map psi. And now basically we are back in this setting which I introduced at the beginning. Of course, the doubling map falls into this setting. And well, we just define h tilde as h composed with xi. And then, well, we just have that we can, what I basically said, that instead of studying this system, we can study what the back measure on 0, 1 of this term. So we just have to prove a central limit theorem on the transformations on 0, 1. And now some words about the Riemann zeta function. So I'm not a number theorist, and I actually think also a number of people here in this audience have more an idea of number theory than me. but I actually used just some basic properties of the Riemann zeta function to apply this. So what is known for, if you look at the fixed S, then if you look at the Riemann zeta function itself, or also its derivative, for going to infinity and minus infinity, well, it behaves chaotically, but it can still be bounded by this term. And yes, just some reference. And so for the special case that S equals 1/2, we actually also get a lot better estimate. And then, well, number theorists don't think this is the best thing possible, so I actually think by linear hypothesis we can put any exponent here. But I mean, well, this is not proven, so I mean, we can't see any. We can't use it to state something further. But yes, as said, if we now look at whatever, if we look at h tilde as the zeta function composed with psi, we are in the setting as before, and we can just try to prove limit theorem on the unit interval. And now I will come to the qualitative central limit theorem, and I will just explain you some of the difficulties to prove it. So, well, I just do some recap, and I mean, well, we have already seen a little bit of transfer operator methods today, but well, still let me keep it slow. So we assume that we have a mixing probability measure preserving dynamical system, and we have a transfer operator which is a unique operator that this inequality holds. Well, I mean, there's also other definitions we have seen this morning. And then, well, we already get the central limit theorem if we have a function in this in a Banach space such that, well, we have some Banach space of functions which is in the L2 space, because, well, I mean, of course, we need L2 to get the central limit theorem, and this transfer operator which we have defined here, well, this is our well, okay, this is supposed to be a t hat and not a psi hat, I'm sorry. It's quasi-compact in this space, and our function f is actually in this space, then we already get a central limit theorem. And well, I just stated this theorem, but I mean, there has been a lot of work before. I'm not going to state each result in this area, but a lot of people have seen results like this anyway. And so the difficulty is now to find a Banach space which fulfills this, so that our, well, this Riemann zeta function composed with this function psi falls into this space. And well, I also want to mention this statement, of course, does not give us a speed of convergence result yet. This we have to do in the next section. And I just give you a recap of some standard Banach spaces. I've been told now that there are a number of Banach spaces which allow unbounded observables. If you think one of these Banach spaces fulfills, is applicable also for the Riemann zeta function, then please let me know. But so far, those which I have checked are not. But yeah, just some, if you like if you look at a very standard space, this is the space of bounded variation, and you just say, okay, you measure how much a function it differs between all the points, and then you take the variation. But well, this is a space you probably have seen. Then well, you can look at the space of quasi-Holder functions. And so if you have not seen this, I just want to define it properly, because what we will do in the next steps will be to look at the space which is derived from this space of quasi-Holder functions. So what we do is to define the oscillation between of a function on some set S as the difference of the supremum and the infimum. I possibly could also take the essential supremum. And then we define the epsilon ball around X, and as seminorm we define, okay, we look at the oscillation of F on some epsilon ball around X and divide it by some epsilon to the beta. And well, I mean, these are long studied spaces. Yeah, and then maybe also have to make a proper norm out of it, so that it's not only a seminorm. And we look at this, and then we define this space as those functions which are bounded. And well, there are a number of people who have looked at these spaces and studied them. And well, but one problem is that these functions have to be essentially bounded if you look at these spaces. So what we, however, this space is quite nice, so it allows you a lot of wiggling around. So what we did then was to use some additional smoothing operator at 0 and 1. So we defined this smoothing operator alpha as x to the alpha times 1 minus x to the alpha times f of x, and then we were looking at the oscillation of this function f, where before we had applied the smoothing operator. And then, of course, I mean, if you have at 0, at 1 a singularity of order alpha, then well, I mean, this thing will remain bounded, and things stay nice. And I mean, what we have seen before with the Riemann zeta function, it is they actually have a pole of some order. And then, well, we define this proper norm, so we don't only have a semi-norm, and give the space a name. And well, now if alpha and beta are sufficiently small, then we have all these required properties of the central limits here, and by having the transfer operator having a spectral gap, and we get a central limit theorem. So at the moment I just write alpha and beta sufficiently small for the following reason. I was studying earlier only this doubling map, so in this case I think it would just be alpha smaller than beta less than 1. And for the general case on which I was working with Casson, and well, I mean, basically we were working on the quantitative version, but in this case we also wanted to have a nicer statement, and well, I mean, only studying the doubling map is quite a boring thing. Well, unfortunately we did not manage to put it on archive until now, but yeah, I mean, I'm positive that we have an archive version by the end of this month. And so this very, at least for the doubling map, and I mean also for a number of other maps, but I would have to state the properties properly. We actually get this qualitative central limit zeta theorem for the Riemann zeta function over the Boolean type transformation. And now I want to go to the quantitative central limit theorem, and now well, this is basically the work where Carson and me started to work together. And well, I mean, Carson had this very nice result with François' pen, and we tried to apply this. So he has a nice quantitative central limit theorem, which is stated in a very general way, and we actually thought it's quite easy to apply it, but then I mean, it ended up that there is need for a lot of technical details. So yeah, I just wanted to state this theorem, also advertise a little bit the work of my colleague. But well, to state it properly, I unfortunately have to introduce some notation first. Or most of that what I'm doing now is standard notation, but well, we still need it. So this psi hat is supposed to be the twisted transfer operator, and for we call this mass frac n the Gaussian density, and then the capital mass frac n the corresponding distribution function. And we look at A as the the expectation of the normalized sum, and sigma squared, it's basically then the variance of the centralized and normed sum. And so now this theorem is, well, basically you will now get a number of conditions, but then you also get a very nice result. So what we were looking at was you need a sequence of Banach spaces all embedded into each other, and they have some technical conditions. So all of and well, these three things are basically the properties which make it not too straightforward to just apply it just any Banach space. So we have to have this transfer operator psi hat is in the function mapping from this Banach spaces, and it's also supposed to be differentiable and continuous. And well, then we need some additional conditions, which however are not that difficult to fulfill. So we also need a spectral, a particular. We have some additional condition on the size of the spectral gap of this transfer operator. And well, chi is also not supposed to be cohomologous to a constant, but well, I mean, this is an often used condition. And well, if we look at the normed sum, this has to be an L2 weakly convergent subsequence. And if we have all these properties, which, well, I mean, they are a little bit technical, but then you get a very nice result, namely you have a quadratic polynomial p, and these depend on the first three symptotic moments of S and chi, such that you get this convergence. So, well, just look at it for a moment. So we look at this probability that this normed and standard sum is less than equal to x minus the normal distribution. You know that, well, that this term converges to this term, right? So, but you don't have any, with the qualitative central limit theorem, you don't have any further knowledge. But then you can say, okay, well, then we have also these polynomials with which we can estimate the speed of convergence. And if you take all these together, this is in little o of a square root of n. So, well, this converges quite fast. Or, well, if you don't know it, this is also called Edgeworth expansion. And well, just to give it, to put it into some reference, if you look at IID random variables, which I mean, of course, is a very strong assumption, then you would basically get the same result here. So, I mean, if we apply this theorem, then, well, I mean, it's quite a strong result. So, I mean, it's even though there are a couple of technical assumptions, it's worth to actually look at them and try to solve all of them. And then, well, and then basically what we did, we checked all these properties and we are fiddling around with the constants, and then we get actually the following result. So we have this transformation, a piecewise expanding interval maps. It's just, I just put down the setting again, which we had at the beginning. And then, well, we additionally need that our chi has to be differentiable. I mean, we think that there's also some possibility that you can get rid of the differentiability, but with some loss of constants. But if this is the case, and then we can give precise estimates on beta, alpha, and gamma, such that if our chi is in this space, then we get this first order expansion. Okay, now I have to say a thing which I'm not so proud of, but usually I try not to present new results. So 1 week ago we found some mistake and we had to recalculate some things, and I'm pretty sure that everything works, but, well, I mean, there might be the possibility that some of these constants change slightly because we have overseen something. But, I mean, it shouldn't be so much of a difference. And so, just some words about the difficulties. Why it's, I mean, right now we have roughly 30 pages, and then I think like, okay, well, I mean, you just apply a theorem. I mean, why is it so difficult? But it ends up that there are just a number of technical calculations. So, I mean, we have, to prove that we have a spectral gap, or that our space is quasi-compact, we need some form of Lasota-Yor, Kenyon-Hervé, or whatever, call it inequality, and well, this we have from the qualitative central limit theorem. But what we need is this embedding from one space to the others. So we also need that this transfer operator here behaves nicely, and it's not only the transfer operator, but it is the transfer operator. So and well, also the continuity. So what we actually look at is this exponential of I as chi, and well, since chi is not a very nicely behaved function, well, there's a lot of technical work to fiddle around what happens if I multiply with a function like this. But, well, just to say something about the difficulties. And because of this, we have to impose some additional conditions on these parameters alpha, beta, gamma, so they can't be as nicely as in the qualitative version. Okay, and with this I would like to close. So this is the references I used. And well, as said, the archive version is hopefully there at the end of the month.